crosstalk or near field coupling, module 4.2. In this module, we will look into capacitive coupling and inductive coupling. First, the capacitive coupling. So the situation is shown here. The coupling is between two circuits, the source circuit and victim circuit. This is the source circuit and this is the victim circuit. We subscript 2 for the source and 1 for the victim. And that coupling capacitance, let's say it is C12. Now we can re-represent this scheme in a more convenient fashion as shown here. So you have this circuit represented here, and you have certain parasitic capacitance from this line to the ground, and also from this line on the victim side to the ground. So these capacitances to the reference are termed as CR, and that is shown here. And between these two circuits, you have the coupling capacitance C12. So this is node 1 and node 2. And we are interested in the voltage, noise voltage appearing across this load resistor RL. So let us do a nodal analysis of this circuit. So the total current at node 1 is 0. So we are interested in how much current will be coupled, will be entering into node 1 due to the sources over here. So we write out the node equations and from that find VL2, and here you have VL1. Then you will get the voltage difference across this. So VL2, you can simplify the expressions and you will end up with an expression like this. These type of manipulations you can do at home, so we will not spend too much time following the steps involved in the manipulation. It is basic circuit analysis. Now our aim is to find certain inferences that we can get regarding the character of capacitive coupling. So to simplify that, to simplify the analysis, we assume that all these resistors are having the same value. Often when we have instruments and all, we have 50 ohms. So let's say that all resistors involved are having a resistor R, a common resistor R. Then in that case we solve for VL1 and VG2. Then we get more simplified expressions that can be handled. So we get an expression like this: VL1 by VG2. This is the transfer function. VG2 is the source, VL1 is the noise voltage. Now in this case, the coupling capacitance C12 is much smaller compared to the capacitance to the reference, and therefore we can neglect these terms that contains CR, and we can see that 4 is much greater than any of these terms. And finally we get the transfer function. Capacitive crosstalk increases with frequency or fast changing voltages because it is proportional to omega. For a given mutual capacitance C12 and disturbing voltage VG2, the crosstalk increases with increase in circuit impedance R. So capacitive crosstalk is more predominant in high impedance circuits, where we have less currents and more voltages. So these conclusions we can arrive at from this expression. That is, higher the circuit impedance, more the capacitive crosstalk. Higher the coupling capacitance, more the capacitive crosstalk. Higher the frequency or the rate of rise of voltage, more capacitive crosstalk. Now, how do we model capacitive coupling? So the relationship between the concept of capacitive coupling and Gauss's law we have seen in chapter 2, which is reproduced here. So if you take a closed surface around it and take all the flux lines epsilon 0 E normal to that, so that will be equal to the charge contained within that closed surface. And if you take rate of change with respect to time of d, then we see that we take this rate of change on both sides. So this is equal to dq by dt, which is equal to I. So we know how to relate rate of change of electric field coming out of an enclosed surface in terms of the current. So we can introduce the concept of capacitance, which is defined as dq by dv. 1, 2, that is the voltage difference between these two bodies. So rate of change of Q with respect to this voltage. So comparing these two, we can see that electric field interaction can be modeled as a current injection. So capacitive coupling can be modeled as a current injection. So we remove the source part of this problem by a current IC, which is given by the capacitance C12 and rate of change of the voltage across it. This is the coupling capacitance. Then V12 is VL1 by VL2, and this source current IC equal to j omega C12 and this potential difference across. So now you write the node equations for I1 here. So the whole thing, the current entering here, we write it as IC. Now this way it is easier to do the analysis, and several sources can be added when respective C12 is known. So you can have one circuit here, then you can have another one current source here, another current source there. So you can have many lines and you can easily connect these sources. Now, methods to reduce capacitive crosstalk. So the first line is to reduce coupling capacitance as much as possible. From the chapter on non-ideal behavior of conductors, that's chapter 3, we have seen what influences the capacitance between conductors. So we have seen that if you reduce the surface area of conductors, you reduce the capacitance between the conductors. Then you increase the distance between the conductors to reduce the capacitance. And you introduce a ground plane close to the pair of conductors. Then you increase the capacitance to the ground. That way you remove a lot of field lines between the conductors and divert them to the ground. So all these things you have seen in chapter 3. For example, conductive planes in PCB, routing of cables to close to metal cabinets, etc. All this will reduce coupling capacitance between the conductors. However, you have to be careful with this type of methods, because if the ground is very dirty due to other heavy noise currents, then some of this noise may be picked up from the ground through the capacitance to the ground CR. So that one has to be careful. Then another way is to reduce the high frequencies or fast rising pulses, to reduce the frequency or reduce the rate of rise dV by dt. Then you can also use metallic screen. So in the case of transformer, you have seen how you are using the metallic screen to reduce the coupling capacitance between primary and secondary coil. So same technique is applicable here. So we will see shielding later in another module when we talk of shielded cable, shielding to reduce crosstalk. Now, inductive coupling, where between the source circuit cables and victim circuit cables you have a Manti-Fill interaction, which is modeled as a mutual coupling M. So same basic three conductor scheme is used. So here you have one circuit, the source circuit that is shown here, then the victim circuit that is shown here. So this coupling between these two lines is shown as some sort of a transformer. L2 is the inductance of this line and L1 is the inductance of this line. Then you have mutual coupling. Then of course one end of RL1 and another end of RL2 are connected together to the ground. So this is the circuit that we will analyze for inductive coupling. So we are interested in voltage across RL1. So that will be the noise voltage due to this source. Now just to aid in the analysis, the dot convention for transformers, because the transformer winding can be done in different ways. So the way the winding is done will influence whether in writing the equations the mutual coupling has to be to have a minus sign in front or a plus sign in front. Suppose you have a dot here and the current is entering, and a dot here and current is entering over there. So this is the sign convention, positive V1, positive V2. So a positive current is entering the dot. Then V2, this voltage is j omega L2, this is the inductance, self-inductance, L2 I2, this current, plus the contribution from this will be positive because both currents are entering the dot. In the same way, V1, j omega L1 I1 plus j omega M I2 because of this dot convention. Now you can have it in the opposite way, where the current is entering but the dot is over here. Then you have the mutual inductance voltage as negative. Now with this in mind, we adopt this dot convention where j omega M is positive, coming as positive. Do the loop or mesh analysis. Again, not going into the details, you can do it at home as a homework to follow the steps and get the same expressions for I2. Then as usual, we want to have some general conclusions. For that, we assume that all these resistors are having the same value, and also we say that your resistance is much larger than omega L. So we can neglect this inductive drop also and keep only the mutual coupling. So with those simplifications, we can write the transfer function VL1 by VG2 as this expression. Then again, from this 4r squared is much larger than all other terms over here. So we neglect that, and approximately VL1 by VG2 is minus j omega m by 4r. So you get an expression that is similar to capacity coupling, but with r in the denominator. What does it signify? It signifies that as r is increasing, this transfer function is reduced. If it is low, this is increased. That is, the inductive coupling is more dominant in low impedance circuits. Magnetic field coupling, that is more conducive in the low impedance circuits where you have the possibility of driving larger currents. That is one conclusion. And second thing is that as before that we found for capacitive coupling, if you increase frequency or rate of change of current, you also increase this noise voltage. If you have more mutual inductance between these two circuits, then also you increase this disturbing voltage. Now, how to model the inductive coupling? We have seen in chapter 2 how to model magnetic field interaction as a series voltage source. That is shown pictorially over here. The Raymond equations also we have seen from Faraday's law. The EMF is the closed line integral of E dot dl. That will be equals minus rate of change of flux linking with the circuit, minus sign because whatever current it produces, it will create a magnetic field that will oppose the original flux, causing this current. So all these things we have seen. So we can connect this Faraday's law to this circuit parameter M. M is nothing but d phi by d I1 in this current. Then that is equal to d phi by dt or EMF. So the magnetic field interaction can be modeled as a series voltage source. This follows from chapter 2. So we remove this source circuit. Now the action of this is coming over here as a voltage source. So in this we introduce a source Vi, and Vi is given by minus j omega mi2, or in time domain minus m di2 by dt, where I2 is the current in the source circuit. Now similarly you can have several other sources, so several other circuits, and all these things can be added up. The only thing we need to know is the respective mutual inductance. So how do we reduce inductive coupling? The first line of defense is to reduce the mutual inductance M. This we have seen while doing well, not exactly the mutual inductance, we have seen regarding the external inductance of circuits and all. So if you increase the distance between conductors, you reduce the mutual inductance also. Then if you reduce the loop area of the circuits, then you have less chance for coupling, less area for coupling. So you reduce mutual inductance. Then coupling is a directional phenomena, magnetic coupling. So you can orient the loops in such a way that one loop surface is normal or is to the other one. So when they are orthogonal to each other, when the loops are orthogonal to each other, you have less coupling also. Then of course you can reduce the frequency omega. So all these techniques can be used for reducing the inductive coupling. Here an example, ribbon cables are very common in all computers and equipment connections. You have several possibilities of arranging signal and reference in that. One possibility is that to reduce the number of conductors, you can have several signal lines and use one common reference. This would be a very bad choice from electromagnetic compatibility point of view, because imagine this circuit at the extreme level. So this will be coupling with all other circuit 100%. So you create, if you have a source here, you create a lot of strong coupling to all other conductors, and you create noise, introduce noise in the other circuits. So this would be a good choice, interspersed reference conductors. So this is one circuit, 2, 3, 4, like that. So you have less coupling between the circuits now. So that's a good choice. And this is the best choice, where you have the signal conductors and a metal plane or foil below. So you have a loop here, but you have very little interaction between those loops. So less transfer of noise. Another way is use of twisted pair cable. So how is it working? So it is illustrated in this particular case, where we have a twisted pair cable of this form, showing one twist only. So in these two conductors, one may be connected to a reference on one end or both ends. Now imagine a current here somewhere far away. So that current will create a magnetic flux. Now here it is going into the plane of the paper all around. Now from Faraday's law, if you have a closed loop like that, it can be a fictitious loop like this, then it can drive certain currents over here, and those currents will produce a magnetic flux that opposes the original flux. So in that way, it will reduce the coupling inside the loops. So this is the way the twisted pair is acting. So you have a EMF around this loop that will be cancelling the original flux. That can in principle produce a circulating current. Now some noise voltage due to capacitive coupling will be still there, because here assume that the action of all these sources will create the loop is like this. So the magnetic field is coming out. So you have a net some current flow over here. So this the current flow here it is connected to the reference, so you have a net voltage drop across this. So this is called unbalanced twisted pair. So due to the capacitive coupling, you can have some net voltage across, because imagine the capacitive coupling, you have a passive capacitance here and you have certain injection. That current will travel in both directions. So here it is from the top. Now in the other conductor it is from the bottom, so they cancel out each other over here. But in this side they will not, because one is connected to the ground. So you will have a net current flow, and that will appear as a noise voltage due to capacitive coupling. So even that, but magnetic coupling is almost completely eliminated. So even that capacitive coupling can be eliminated if you use a balanced twisted pair. The idea is that don't connect the resistance directly, but some sort of a transformer where central part is connected to the ground. Then when you have this capacitive coupling, the currents are injected here and coming to the ground, positive and negative, and the currents are injected into this. So they are balanced over here in opposing currents. So the net current induced will be, net noise voltage induced will be 0. So you eliminate even capacitive coupling. So balanced twisted pair to minimize both inductive and capacitive coupling. So now we have seen common impedance coupling, capacitive coupling and inductive coupling, and derived the models for that, simple models for that, and seen how we can reduce those crosstalk. For example, with common impedance, we can minimize the common impedance or completely eliminate that. So this can be done by avoiding sharing long grounding cables and planes. So that will reduce common impedance coupling. For capacitive crosstalk, first we can adopt all different techniques to reduce the coupling capacitance in the form of introducing a ground plane, controlling the dimensions of conductors and distance between them, etc. Then we can avoid high frequencies. We can use shielded cables with at least one end grounded, which we will see later. Then inductive crosstalk, where we can control that by reducing the mutual inductance. Example, by reducing the loop area, orienting the loops perpendicular to each other, etc. to reduce the coupling. Then we can use twisted conductors or twisted wire pair. And also avoiding high frequencies will reduce inductive crosstalk. So that ends module 2.